All right, I think we should probably just start right now. Should we start with just doing some problems? Any particular mastering physics problems you guys would like to see? Yeah, we can do that. And part B, potential charged annulus. All right, I'll get that lined up. Great. All right, I think we did the charged annulus in class, but we can do that again. All right, let's start by reviewing electric potential. All right, so we're talking about electric potential. I guess there's two ways to look at it when you're looking at electric potential. Okay, you can relate it to electric potential energy. So you have a positive charge. Well, let's say you have two positive charges, right? And you try to bring this charge in, and so they're going to push against each other. So if this is some change in position, and then this is going to push against it, force that experiences. Right, the work done by this electric force, this Coulomb force, it's going to look like this. Right, how much it goes, or I guess, when we say delta x, it's going from some position well, x1 to some x2 or something like that, right? And so this is going to relate to this negative change in potential energy. And so what we're doing here is, I think the outcome of this ended up being that you essentially have a potential energy function when you have 2 point charges equal to this. Sorry, not negative, just positive. Q1, Q2 over R squared, which is the separation. Oh no, sorry, not R squared, just R. Just R. Okay, when you work that integral out, if you want to see that, we can work that out too. But pretty much, if you start from potential energy, you have a potential energy function, then you use this relationship that the electric potential is U divided by Q. So if this is Q of the source, and this is like your test charge Q. So I guess if you want to kind of write it like that, so instead of using Q1, Q2, we can say Q of the source, then times Q test charge. What you're doing is you're dividing away this test charge. So that, again, oftentimes when we talk about then what is the potential on this spot due to the source charge. So this would be the potential due to the source, right? That's then what you get is just K Q the source divided by R. Okay, so that's looking at it in terms of potential energy. So you have the potential energy of this charge brought in from infinity to this spot is dependent on the potential on that spot due to this charge, right? So potential is just a value of the spot, but the potential energy is associated with the charge that you put into that spot. The other way to look at potential is to, instead of looking at it in terms of potential energy, is to look at it in terms of the electric field. So you get that the change in the electric potential is equal to the negative integral of the electric field over some positional change, right? The negative of it. So there are a couple things that this is essentially saying is that if you have some electric field, and you look at two spots along the electric field, right? Maybe point A, point B, that if you go the separation S, or however, whatever path that you take, right? You talk about the dot product. So you're looking for how much of the electric field is actually pointing in the direction of your displacement from A to B. Then that product, E over that distance, leads to some potential drop. That's why it's a negative, right? So usually the easiest example of this is we look at parallel plates. So this is positively charged. This is negatively charged. The electric field will point this way. Usually when we look at plates, we're looking at a uniform field. Okay, so this electric field, there's some separation here, D. Okay, and so if I'm going, let's look at 4 different points. Okay, let's look at this point, this point, this point, this point, A, B, C, and D. Okay, so if A and B take a path that is perpendicular to the electric field, right, then the change in voltage from A to B is 0. Okay, if this line is perpendicular, right, then there's no electric field along the path from A to B, so there's no potential change. Right? You only get potential change in the direction of your electric field. So if I go this way, let's say from A to D, right, whatever this separation is, I'll call it S or something like that. Then the voltage change from A to D will be your electric field times S. And how this integral turns into that, and actually it should be a negative, how that integral turns into that is a couple assumptions. If E and S are in the same direction, right, then the dot product gives you like cosine of 0, and so you get the full thing. You don't have they're parallel, right? So the dot product works out to just be products, and then also because this is a uniform field, this integral simplifies out because your electric field is constant, so it goes out of the integral, and then you just multiply. So that's why it's just ES. And then it's negative because it's in the direction from A to D is a drop, so you lose potential. Now, if you go from A to C, okay, actually, this potential drop will be the same as this one. If this is like, if you imagine this to be on the same horizontal displacement. If C has the same horizontal displacement as D, then actually the electric potential is the same, because, or the potential drop is the same, because even though this is a longer path, when you do the dot product, right, in terms of how much is E, the electric field, is only horizontal. So the displacement that is in the direction of E is the same as it was from A to D. Hopefully that makes sense, right? They are the same. Whoops. Same if horizontal displacement is the same, right? Basically, it's only the displacement in the direction of E that actually matters. Any perpendicular displacement doesn't matter. That's why this voltage drop is 0. Well, yeah, it really depends on the problem. Most of the time, well, if you can pick out the particular problems that you have trouble with, they'll maybe make it easier to figure out what context to help you, because it's true. This is a very general concept, and there are a lot of different particular cases to look at, and can make it difficult to apply it. Yeah, when you find those, then we can take a look. Let's go ahead and do the one that Nikita was asking about. This. Okay, so we're looking at this problem, right? This one. Okay, so you got the annular ring. It has a certain surface charge density, or not. It's an annular ring, so it's not just a small thickness on this dimension. It's actually kind of thick, right? So it has an outer radius, inner radius. The symmetry, we kind of talked about this in class. We're looking for, as shown in the figure, which set of points makes the same contribution toward the potential calculated at any point along the axis of the annulus, that's along the center, essentially. You're looking for points that are all equidistant to the center. Or if you want to kind of imagine this z-axis sticks out of the page. So x and y is the plane of the annular ring. I mean, z sticks out of the page. So we want to figure out what is the electric potential at some point z away from the center. And so we want all the points that have the same contribution towards the potential calculated at that is B. Okay, all those points are going to be equidistant from the axis. So this is the hard part that we went through in class. How do you determine the electric potential at that spot? And so let's take a look. I gotta pull this to the side here. Okay. So first, let's do our diagram. Okay, so I'm gonna try my best to draw an annular ring. Okay, so then here's the center axis z. Here's x. Here's y. Here's z. Okay. Actually, you know what? Let me make this bigger. This is too small. It's really big. So big ring. inner radius. Here's z. Here's x. Oops. What did I do? Okay, x, y. All right. And so what we're going to do is, if there's some point on here, we'll call this point P. Some point P that's on the axis, some distance, z away from the center here. All the points along a slice that I'm going to make. I'm going to make a slice at some radius r away from the center. And that's going to have a certain thickness to it that is infinitesimally small. So we can add up all those slices. Okay, so this slice is going to have some thickness dr, and that is a distance r away from the center. Okay, so the reason why we want to do that is because every point along this slice is equidistant to P, right? This is some distance to P. What is that distance? Let's see. I'm going to call this some distance d. Let d is equal to the square root of r squared plus z squared. Right, that's using Pythagorean theorem. And if you can imagine rotating this triangle all the way around, it's the same triangle for each piece. So this piece, this slice, contains a certain amount of charge. I'm going to call it dq. And it covers over a certain area, dA, and that the ratio of dq to dA is... See, it's supposed to be drawn like this, right? Has that surface charge density sigma, right? Charge to area ratio. If it's uniformly charged, charged, then that's equal to sigma. Okay, and so eventually, because this whole element is equidistant to that point, the voltage at that point, due to the contribution of each piece, well, I guess you can kind of do it like this. Each piece, okay, if you take like an even smaller slice, just like a little piece right there, contributes some dV that is k dq over r. Okay, and what we're saying is, if you add up all of those little pieces in this particular ring, they will all add up to be the same thing, a k dq over r, where in this case it'll be dq of the whole piece. A second. Okay, does that make sense? That whether I use just a little dot or I use this slice of a ring, it's still k dq over r. That doesn't make sense, just let me know. I'm watching the chat here. Okay, so that means that we can represent dqs by that ring. Okay, and then I'm going to add up all the rings working from the inside out. And if I'm going to do that, I need to change from a dq into some sort of dr. Right? I need to match the variables. So dq will equal to sigma dA. And the area of that little slice is 2 pi r dr. So that's what I'm going to plug into that. So I get k sigma 2 pi r dr over r. Why does that seem kind of weird, actually? Let me see. Oh, this r is different from this r. I have to be careful. This is supposed to be d, not r. Right? This is actually supposed to be the distance from the point, from the charge to this point P. So actually, yeah, you gotta be careful about that. This is d, but this is r. This is actually the r, which is the radius of that ring from the center, whereas the denominator here, this is supposed to be the distance from the point charge to this point P. Okay, so they're different. So actually, if I substitute for d, I can write it kind of like this. Let me pull all my constants out to the front. 2 pi k sigma r over square root x squared plus r squared dr. Okay, so that is how much voltage, a little infinitesimal amount of voltage I get from this little geometric slice. Okay, so now instead of looking at it in terms of a slice of charge, I'm looking at it as a radial piece counting outward, right? This ring. The x squared comes from using Pythagorean theorem. Oh, sorry, you're right. It should not be x, it should be r squared. Yeah. Sorry, it should be, gotcha. It should be r squared plus z squared. Yeah, totally writing that correctly. R squared plus z squared. There we go. Yeah, not x squared. You are correct. Yeah, I'm trying to take this and then just put that there. Yeah. Okay, so I'm going to go ahead and rewrite the whole thing down here. So dv equals to 2 pi k sigma and r square root r squared plus z squared dr. Okay, and now we integrate this. We're going to add this all up. Okay, now this is going to add up from r2. Hold on, let me look at the problem. Is it r1 to r2? Let's see. It was from r1 to r2. Okay, so we're going to add up from r1 to r2. Okay, r1 to r2. Okay, and then this is just going to be the total sum of all the voltage contributions. So V will equal to this. And to solve this integral, I believe you just do, it was use substitution. So it would be r squared plus z squared. So that du equals to 2r dr. Okay, so then this we can substitute, or in other words, r dr equals to du over 2. So we can substitute that 2 pi k sigma from, we talked about this in class. We'll come back to the limits of integration. You would substitute r1 into this, and then your limits would be from u1 to u2, but when we substitute back, it won't really matter. So we'll come back to this. So this will be, let's see, u to the negative 1/2 du over 2. Okay, that is the u substitution part. Yeah, we can get to those problems, no problem. Okay. Any questions about this? How we got this part? The u substitution. So then we go ahead and integrate that out. So this ended up being, well, actually the 2 is going to cancel with that 2, so we can actually get rid of that. So this will be 1/2 u to the 1/2. All right. No, sorry, it'd be 2. 2u to the 1/2. Yeah. Integrating from, well, again, we'll come back to the limits of integration. Let's go ahead and substitute back in for u. U was this. So this is 2 pi k sigma square root r squared plus z squared. Now we're pretty much going back from R1 to R2. Okay, so we should get that V is equal to this 2 pi k sigma. Substitute for R2 and then subtract R1. So this will be square root of R2 squared plus Z squared minus square root of R1 squared plus Z squared. And that's it. So you can either do it, let's see, I think in the problem it wanted it in terms of K and not E or epsilon. Let's see. Yeah, use K. So it was like 2 pi k sigma square root R2 squared plus Z squared, and then minus another R square root R1 squared plus Z squared. And I think that was it. What did I miss? Let's see. Squared plus Z squared. D instead of Z. Oh, did it have a specific distance? Oh yeah, distance D. Okay. So D. Yeah. You are correct. Yeah, hopefully that's not too confusing in terms of it wanted to use D for a distance D away from the center. I use D as the hypotenuse. I think you can go back and look at as long as you understand what I'm using with my variables, and then you can substitute D for Z. So, questions about these steps? Again, I think it's very unlikely you'll have to actually integrate something like this, but yeah, I haven't really seen anything this crazy. I mean, it's good for you to know how to do it for certain. At least if you can set up the integral, you'll get most of the points. Okay, so let's save that. And I'll upload these pictures onto Google Drive. So we can move on to the next one. 30.45. Let's take a look. Okay, how much charge passes through the starter motor? I think I can do it like this. So I think I can write on here. Let's see. Okay. Starter motor has a certain amount of current. Okay, so how much charge passes through? I think this one's pretty much just using current. So 120 amps means it's 120 coulombs per second. So if it runs for 0.65 seconds, then the total amount of charge passing through, which should be 120 times 0.65, Okay, and that works out to be 78. So that should be 78 coulombs. Okay. And then how far does an electron travel along the wire while the starter motor is on? So here you're going to have to look at, let's see. I think this is the one where you want to use, what was it called? It's something like, so the number of electrons passing through should be the number density times the area times the drift velocity. Okay, so the drift velocity, you can kind of think of that as like some length measurement, some displacement over time, right? So you can look at like this. Whoops. So it's going to travel some distance over some amount of time t. Right, so then if this is the electron current, then the actual current, whoops, is just going to be the same thing times the charge of an electron. So this will be Ne, charge of electron, cross-sectional area, displacement over time. So this is kind of what it's looking for, right? How far does an electron travel? We're trying to solve for x, or this delta x. Probably you won't run into this. I find it, I'm like 100% positive. They're not going to ask you to memorize what the electron density of copper is, but because this is a book problem, this is going to come from using the book. And in the book, let's see, it gives you a little table of the charge densities of different materials. And this is on page 869. So page 869, it says for copper, it is 8.5 times 10 to the 28 electrons per cubic meter. Okay, so that's essentially what so if we're solving for delta x, then it's going to be I times the amount of time that passed by divided by this density times E times the cross-sectional area. So it gives us the diameter. So cross-sectional area is going to be pi d over 2 squared. And that should give us delta x, because that's what we're solving for. So yeah, if you're 120 amps times this 0.65 seconds divided by this electron density, 8.5, times the charge of electron, times pi, times this diameter, which is 5.5 millimeters. So I'm just going to do 5.5 times 10 to the negative 3 squared. And so let's see what that gives. Oh, this is kind of a pain to do. I wish there was a way. Let's see here. I'm just going to save this for now. So, okay, now I can plug this all in. Let's use. Yeah, I got that value from the book. It's on page 869 on the right-hand side. It's kind of a small table, but it's table 30.1. It says for copper, the electron density is 8.5 times 10 to the 28. Okay, so I'm looking at 120 times 6.65 divided by this thing. That looks pretty good. Okay, so this number, we will put it in. Point zero, whoops, 0.00024 meters, or 0.24 millimeters. Okay, so probably the two things that will probably catch you on that is knowing to use. Let me bring this back up. Knowing to use this equation. The I equals NE. I think they have this one, okay, in the equation sheet, but it doesn't use delta x over delta t. It just says VD, the drift velocity. But you just kind of have to understand that the drift velocity is how far along the wire it travels in a certain amount of time. That's the drift velocity. And so if we want to know how far it has traveled and we know how much time has passed by, then we can solve. Okay. Questions on that one? Right. Next one, 27.38. Let's take a look. 27.38. I think we did this one in class 2. Okay. Yeah. Let's take a look at. I think what will really help with this is a diagram. So let me pull this up. Okay, so we'll diagram this. A hollow metal sphere has some inner radius A, some outer radius B. So inner radius A and some outer radius B. Okay. And the hollow sphere has already 2q plus 2q. And then you put a point charge of plus q on the inside. So yeah, some charge here, which is plus q. Okay, so what we're going to do is we're going to do a variety of different Gaussian surfaces to solve for what the electric field will be in those different regions. So actually, I think I made this a little too small. I'll make this bigger. So here's inner radius A. And here's outer radius B. So determine the magnitude of the electric field in region R less than A. Okay, so we're going to do Gaussian surface. And this encloses a charge plus Q. Okay, so when we do Gauss's law, we're looking at, I'm going to do the full thing once, and then after that, we'll just take shortcuts. Okay, so first, this is the full thing, right? And actually, there's the closed integral. So we're looking at the flux through the whole surface. Yeah, we definitely will have time, so we can get to all of those in a minute. Focusing on this one. So first, because it is a sphere that is matching the because it's a sphere and it's a point charge, your electric field will be everywhere parallel to this A vector. So by shape, or due to shape, this becomes this. Okay, you can get rid of the dot product. And then by symmetry, meaning that because every point on the sphere is an equal distance from the center, this E is going to be constant everywhere. You can pull it out. Okay, so then essentially this becomes E 4 pi r squared, because this is the area of that Gaussian surface, and then is enclosing a charge Q. And so we just solve for E. So E as a function of R is going to be Q. And when you divide both sides, you essentially get KQ over R squared, right? And that's pretty much Coulomb's law. And so you can see here, the answer I have already is, this is K. Well, it's essentially K. I guess we can't use K because it wants it in multiples of Q over epsilon naught. So we will not use K. We'll keep it with the epsilon naught. So we will keep it 1 over 4 pi r squared. And here's the epsilon naught. Okay, so that's the first one. And then, okay, so you can kind of look at that work. Go ahead and save it. So we can look at the next part. So the next part, right? What is the electric field in the region of where you're inside the metal sphere part between A and B? That's just 0, right? Because if it's a conductor, there should be no electric field in the conductor. Once you get outside the conductor, if you look at your enclosed charge, okay, how much charge are you enclosing in this? Where here's, your sphere. This is Q, but then your charge sphere also has plus 2Q, right? So when you take a Gaussian surface outside the whole thing, right, you're enclosing this plus Q and you're enclosing that plus 2Q. So if you go through the whole derivation again, you end up with the same left-hand side because it's the same Gaussian surface, but just bigger. But now the enclosed charge is 3Q. Right. So when you divide both sides by 4 pi r squared, you still have the 4 pi r squared, but now you have 3 of these, and so you have 3Q times epsilon naught. Now, how do you figure out how much charge is on the inside of the sphere and outside of the sphere? So, just looking at part D, how much charge is on the inside surface of the hollow sphere? So when you do your Gaussian surface inside the sphere, because the electric field through your Gaussian surface has to be 0, there has to be no flux through this sphere. And you do the symmetry stuff, yada, yada, you find that there's no electric field here. It must contain a net charge of 0. So how can it contain a net charge of 0? It's only if there's a negative Q right at the surface, the inner surface, so that this negative Q cancels with that positive Q. And so that's where we get the negative 1Q. Okay. And then we'll kind of work our way out. Right. And then, so how much charge is on the exterior surface? There's a couple of ways you can solve this one. So if you have a negative Q on the inner surface and the sphere has a net charge of plus 2, then the outer surface must have plus 3. In other words, what was initially a neutral sphere, right? Imagine that there's, it doesn't mean that there's only plus 2 positive charges on here. There are negative charges and positive charges in here, but there's an imbalance. There's 2 more, a net 2Q more positive charges than there is negative charges. But there's still negative charges in here, right? And so as you put a positive charge in here, what that does is it pulls in the negative charges, even more negative charges into this inner surface, causing the outer surface to be even more exposed, turning it into plus 3q on the outside. Right? Those negative charges will be pulled in from the outside, making the outside even more charged. So the net charge is plus 3 minus 1, right? So that makes a net plus 2. Or you can also do a Gaussian surface out here, right? The net enclosed charge must be plus 3. So plus 3 minus 1 plus 1, that makes plus 3. Any questions on that one? Cool. We'll just keep going then. Next one was 30.6. So let's take a look at 30.6. That's not it. Okay, so this is going to be very similar to the previous wire charge one, where you're going to want to look at the table on 869 to answer this one. Let's see. Okay, how many conduction electrons are there in that much? Yeah, this one is, here, I'll do this. So if little n is that density, okay, and we're looking at gold, that density is 5.9 electrons per cubic meter. Then big N is going to be the total number of conduction electrons that are in this space. So it gives you the diameter, it gives you some length, right? So if you want the total, that's just going to be the density times that volume, or alternatively, that cross-sectional area times some length. And so it's going to be this times, the pi diameter over 2 squared times that delta x. You just got to be very careful about all these dimensions because this is really small. I would highly suggest using scientific notation for all of this. So let's see. You're going to want to do something like this. What's that do? Go back. Okay. So it's asking for that. So we want the density, 1.9. We want the area. So notice, again, to take advantage of scientific notation, I'm just going to do 3.5 e negative 3 so that I don't have to, worry about conversions here. I just use the scientific notation to convert for me. That's the diameter, so I have to divide by 2, and then times this length. And so I get about that many electrons. 1.14 times 10 to the 23rd. Okay. All right. And then how far must the electrons move in the wire to deliver that many coulombs of charge? Okay, so if we have this many electrons, now it's trying to get us to figure out the total charge instead of the number of electrons. So again, here we're solving. We want to know how far it travels, so we're still solving for delta x. But now instead of looking at how many electrons, we want to look at how much charge. So what we're looking for is something like this. Okay, so if the number of electrons is this, then this is the number of electrons, then the charge that's in that should be like this or this. And I want delta x. So delta x is equal to q over NE. Okay. Now, again, you're not going to really see these equations written out like this. They're all kind of rewritten derivations of each other. What you really need to be able to do is look at the variables and understand what they mean. So if I look at just this and I understand this to be a density, then it kind of needs to be intuitively understood that then to get the total number, I take the density times a volume. And then if that's the total number of electrons, if I want to know the charge of those electrons, I should take those number of electrons and multiply by the charge of each. Right? So you're not going to see this in your equation sheet so explicitly written out. You're going to need to kind of have some intuition as to the meaning of each of these variables. Anyways, so this is going to be like, let's see. I'm just going to, it says negative, but we're just looking for how far they have to go to create this much charge. There are electrons anyway. So this is like a 29 times 10 to the negative 9 over this density, which was 5.9 10 to the 28. Charge of 1 electron times that area. Right, something like that. So let's do it. Uh, 29 divided by this thing. Let's see, here we have n, we got the area, and then we wanted the charge of the electron. So something like that. Yeah, so little I is the actual number of electrons. Okay, is the flow of the electrons themselves. So I don't know if I can bring that back up, actually. Let's see. Well, here, I'll just bring it up here. Okay, so this, oh, I didn't do it here. Okay, just kidding. Let's do this. Okay, so little I, which is usually written like this. Okay, this is the number of electrons per second. Okay, the actual flow. No, you do not have to memorize the resistivities. You don't have to memorize the densities of any of those. You just have to know how to use them. Okay, so if I give you that information, then you should be able to use it, or it could be something that you ought to be able to solve for. So if I give you the current or electron current, and I give you some dimensions of a wire, things like that, you ought to be able to solve for it. but this little I is the number of electrons per second. So let's say I have a wire and I have these electrons floating around, okay, and they're all kind of drifting by some drift velocity. If I average everything out, right, there's some drift velocity, and I have this counter, and there's a guy here who's like counting electrons, right? How many electrons pass by? That is I, little I. Okay, how many electrons pass by? So, you count it for 1 second, and then you're like, hey, 5 electrons or something like that. So then I would be 5 electrons 1 second. Okay, that's little I. Big I is how much charge is passing by. Okay, so big I would be each electron has a charge of 1.6 times 10 to the negative 19 coulombs, right? So you have 5 charges, 5 electrons pass by. So 5 electrons per second times each electron has 1.6 times 10 to the negative 19 coulombs in 1 electron. So then you would have like, hey, 8 times 10 to the negative 19 coulombs pass by in 1 second. Okay, that is the difference. Big I is the charge that is passing by per second. Little I is the number of charge carriers or electrons passing by. Okay. Makes sense? Questions? All right, go ahead, save that. Okay, let's see, which one was next? So that was 30.6. Let's take a look at 27.29. Oh yeah, okay, so we're looking at flux again. So let's see. You have the area of this shape. Oh, it's a cube. Okay, so it's a 5.5 by 5.5 cube. What is the electric flux through the side? Okay, so it gives you the angle, right? And so you're looking for, when you're looking at flux, you're looking at, well, here, actually, let's do this. First thing we should do is establish your area vectors. Which directions do the area vectors face? So if you have a cube, looks like this. Okay, your area vector always points outward. That is the convention. Okay, so let's say on the front face, your area vector would point out. On the side face, it would point out like this, like out the left. This would point out the right. It would point up out the top. This would be out the back. And it would be out the bottom, like this. Okay. So that would be your area vectors on each, points outward. So if your flux comes in at an angle through the left side, okay, it is, in other words, if my coordinate system were like this, here's X, here's Y, and here's Z. If you can imagine, Z is pointing out the page. Okay, so Z is in the direction of this one. Let's go ahead and number these, right? So 1 is this side, 2 is the top, 3 is the right, 4 is the bottom. We'll call the front number 5, and we'll call 6 in the back. Okay, so 5 points in the z-axis, 3 points in the x-axis, 2 points in the y-axis, 6 points in the negative z. Okay, so we can actually write all these out. 4 points in the negative y, and then 1 points in the negative x. Okay, so if you can imagine each of these faces pointing in a different direction along those axes. Okay, so your electric field makes a 30-degree angle with the x, or you can say it makes a 60-degree angle with the y, right? So here's x, here's y. Oops. Right, so this would be 60 degrees. Okay, so the area of each face is, we'll do it because it wants it in square meters, so we'll do that area in square meters, 0.055 times 0.055, because it's in centimeters. Okay, so the area of this, each face is 0.003025 square meters. Okay, the electric field has a strength of 500 newtons per coulomb. Okay, so their flux is going to be the strength of the electric field times the area times the cosine of whatever angle is being made with that face. Okay, that the area vector face. Okay, so if it is going into the box, or I'll put it this way, if E points in the opposite direction of A, right? So if you look at face one over here, face 1 points to the left, but E goes to the right. So technically, if you want to look at the angles, EA cosine theta, it's this angle, right? This angle would be like 150 degrees, right? Between A and E, or between E and A. That's 150 degrees, which is equivalent to, so cosine of this is the same as the negative cosine of 30, right? Because it's, they're opposite each other. So you can do that and kind of just go through the trig for each face. So in the end, it's essentially the cosine of the angle that's changing. Because the size of the areas are all the same, the strength of the electric field's all the same, I can go ahead and calculate EA first. So this is going to be 500 times that 0.003025. So this is 1.5125. Okay, so then I'm just going to scale this with all my angles on all my sides. So let me save this real quick. Then we can go through all the calculations. I had to do that because every time I close out of this window, it loses all my writing. So I can't keep it. Okay, so let's look at each face. Face 1 is the left-hand side. It is essentially, you can do cosine of 150, or you can do the negative cosine of 30. But 1.5125. I'm not sure if I wanted to do the cosine in degrees. Okay, good. So it does it in degrees. So it's a negative, right? It should be, the convention is flux going out of a container or out of a closed surface is positive, but on the left-hand side is going in. So that will be a negative 1.3. Okay. But on side 2, which is the top, it's going out. Okay, if you look at the angle between the area vector, which is straight up, and that angle, that would be 60 degrees. So you want the cosine of that. Okay, so that ends up being 0.76. Okay, and yeah, why 500? The strength of the electric field is 500 because it's EA, right? So here's E, it's 500. And then A is the area that we calculated, the 0.003 something. Yeah, it gives you the strength of the electric field. Okay, phase 3. Phase 3 is the right-hand side. Now the angle is 30. Oops. Okay, so we will do 30. Should pretty much just be the positive version of that first answer we had. So 1.3, right? So now whatever was going in on the left-hand side goes out on the right-hand side. And you can pretty much argue the same thing for phase 4. Phase 4, it's instead of going out at the same angle as was on phase 2, is now going in on the bottom. So that's a negative 0.76. Okay. And so what is the net flux? It is 0. Okay. The idea here is the field is being generated outside of the container. And so there is no net flux through the container. Yes, there will be energy-based gravity stuff on the test. Gravitational potential energy. So we had basically everything we did with electric potential energy applies to gravitational potential energy. You just do it like it's a positive and negative charge, right? It's attractive. So we talked about how when you have an attractive force, you have negative potential energy, right? The closer you get, the more negative it is, and it has that kind of inverse graph. Let's see, is this the yeah, this is the last question you guys asked for, so I can answer Paul's question here, and we can come back to this if you have questions on this. But the idea was, right, we did this for gravity. If you have some mass and some big mass, and it's an attractive force, it's the same thing for a positive charge and a negative charge, or whatever, opposite charges, right? And what we said was, if there's some separation here, since the force is this gm over r squared, what you get is that the potential energy becomes gm over r. Okay, and then that the gravitational field becomes g big M over r squared. And so then, well, actually, we never talked about a gravitational potential, but you can argue there's kind of like a gravitational potential as well. So like a V gravity would be like a G. Oh, this should be negative. Sorry, that was actually the whole point of me doing this, was that this ended up being negative. This would be negative. And so then for electric force, this was like a K Q1 Q2 over R squared. So you get this potential energy, K Q1 Q2 over R. Then the electric field, so there's gravitational field, there's electric field, is like a KQ1 over R squared. So then this electric potential is like a KQ over R. So when you graph this, okay, now this is all for point charges, right? This is all for point charges or spheres, uniformly charged spheres. But we'll just kind of keep going with that. And I think I gave you guys these graphs before, the TLDR kind of graphs. But you have some object with some mass, with some radius, big R. And then the force from gravity, this was linear, and then inverse square. Right? And then that the potential energy for this, sorry, my hand's getting a little tired. Potential energy, let's see, this ended up being quadratic and then inverse. Because, and you can figure that out because it's supposed to be, this is supposed to be the integral of this, right? So you integrate an inverse square function, you get an inverse function. You integrate a linear function, you get a quadratic function. And then when you look at potential, as opposed to potential energy, or you look at the field instead of force, it's the same pattern, right? The only difference is you're dividing away the test charge or test mass, right? The pattern is the same. It's still inverse. It's still inverse square. It just gets scaled down. So you're gonna get the same pattern. So what makes the gravity similar to electric fields? You just imagine if this was a negative, right? If this is negative, then that's negative, and then you have an attractive case, which is what gravity is. It's always attracting. Cool. Sweet. Okay, 30.55. Take a look. Okay, you got two wires made of the same material. But it changes. Okay, so what is the current in the 2 millimeter segment? Okay, so I think there's actually a couple ways we can go about doing this, but let's take a look. One thing that absolutely has to be conserved is the current. Okay, the current has to be conserved because you can't have more charge passing by per second. But you can actually have, well, what you'll find is that you have the same current passing by per second, which means you have the same number of electrons passing by per second. But because the second wire has more area, they don't have to flow as fast, right? Because you have a lot more electrons actually passing by per cross section. Well, let's just take a look at how that works out. Okay, so what is the current in the 2 millimeter segment? It should be the same. Okay, so that one I think is actually pretty straightforward. You can't have more charge going through here than you have coming in. That's essentially Kirchhoff's loop rule. But let's look at what is the electron drift speed in this one. Again, you can actually answer this conceptually as well. But let's look at the equation that is relevant. The equation here is the current is equal to this NE EA v drift, right? So if the current has to stay constant, if your area goes up, your drift velocity must go down, right? So by what factor did our area go up? The diameter doubled, which means that the area is quadrupled, right? Because we're talking about area. So if the area quadrupled, then my drift velocity must be cut by a fourth. So if it was 2 times 10 to the negative 4 meters per second, then it's going to be 0.5 times 10 to the negative 4, right? So you don't even have to plug anything in. You can, but that's really kind of ends up being a waste of time because you can take advantage of this proportional behavior. Okay, so let's take a look. If we could just divide this by 4, we should get the right answer. So 0.5. Let's see. Oh, micro. That's stupid. Micrometers per second. So 500. Or is it 50? Wait, am I 0.5 times 10? It should be 50. There we go. Okay. Yeah. There we go. Micrometers per second. Kind of throw a curveball on the units there. Oops. Okay. So that makes sense. Just kind of look at the ratio. And you may see multiple choice questions like that, where if you kind of understand the equations and how the scenario is used in the equations, proportionality can save you a lot of time. Yeah, that is correct. So if the current changed, okay, let's say you have 2 amps going in here. And you had 1.5 amps coming out. Where would that extra 0.5 amps go, right? That you have to have, no matter no matter where it gets, whether it gets thicker, thinner, even if you change materials, right, you still can't just lose charge unless it's being neutralized at some rate. That charge has to go somewhere. So the current will always maintain the same. That is essentially Kirchhoff's junction rule. Let me see if I did that one yet. 46. Did we do that one? I don't think we've done that one. Let's see. Thank you. Oops. Okay, let's do this one. Okay, uniformly charged ball for radius A and charge named Q is at the center of a hollow metal shell. Okay, the hollow sphere has some charge on it. It's very similar, but it is... it's similar, but it's negative Q instead of positive Q. So everything we did in the previous problem, it's going to be the same, except that now it's a negative charge inside instead of a positive charge inside. So let's see. What is the electric field? You're going to do pretty much the same as before. But now it's negative. And let me see if I can pull up. When was it? It was this one. Before this one. This one, right? So when you do Gauss's law, right, you have your sphere, your charged sphere. Here it says it has a hollow metal shell with some inner radius and some outer radius. So this, I guess, is a little different because the ball has some radius a, whereas in the previous problem it was like, I guess, kind of like a point charge. But we can treat it very similarly. Actually, let's look at this question here. This is actually looking for the electric field inside the ball itself. Okay, so that actually makes it a little different. That's going to be more like this scenario, right? We're going to be in this region inside here. So actually that ends up being linear. Let's go ahead and do Gauss's law on that just in case, just for practice sake. So here we have, first we have a ball, radius A, is uniformly charged ball. So it's essentially going to be like an insulator where all the charge is evenly distributed throughout the entire solid ball. And then we have our metal shell, and that shell has some inner radius B, some outer radius C. And the first thing we're going to look at is the Gaussian surface inside a ball, inside the ball. Okay, so this one is a little trickier. So we'll do our Gaussian surface. We'll look at the flux. The flux is equal to the enclosed charge divided by this E. We do all our arguments, the shape and the symmetry. So the left-hand side is 4 pi r squared. And then r is like this radius r. But what's going to be different is this q in is not just q. The q in is the q inside the Gaussian surface. So what we're going to have to do is we're going to have to say that the ratio of the enclosed charge to the enclosed volume, if it is uniformly charged, is equal to the total charge divided by the total volume. Whoops, that should be cubed. Does that make sense? We're assuming uniform charge density. So this is the charge, the density inside the Gaussian surface. And this is the charge density of the whole thing. Right? And what we're saying is if it's uniformly charged, then these should be equal. Okay, if it's uniformly charged, these should be equal. We want to know what Q in is in terms of big Q. So Q in, the 4/3 pi's will cancel. So essentially what you get is Q r cubed over a cubed, right? So it's essentially this ratio. So this will be Q over epsilon naught r cubed over a cubed. Okay, so when we solve for E as a function of radius will equal to, it wants us to do it in factors of Q epsilon naught. So I'm going to keep Q epsilon naught by itself. This r squared will cancel with two of those there. So this will be r over 4 pi a cubed. Okay, so here's the actual expression. We see that it's linear, but what is the actual expression? Turns out you got to keep track of this a cubed. It's going to be part of it. Okay, so let's try and put that in. R a cubed. Oops. And it's also going to be negative, right? Because it was all a negative charge. So make sure you keep track of that. Any questions about how to use Gauss's law there? Gauss's, let's see. Yes, if it was a conductor, then the field would be 0. So when we're looking at this diagram, this works for gravity because there's no such thing as like a conductor for mass. The mass just gets, or for gravity, because it just gets stuck. So the equivalent of this would be an insulator. If you have a conductor, then you just have no field, and then it jumps up. Okay, so determine electric field strength. Now we're looking from A to B. That is between the sphere and the inside of the conductor. Now it's going to behave. You're not in the sphere anymore. You're like in the empty space between them. So that is like, we're in this space between A and B. So you do your Gaussian surface there. Your enclosed charge is just negative Q the whole time. So this ends up being negative 1 over 4 pi r squared. Okay. As I'm doing these, and you're not sure where I'm getting these answers from, just go ahead and say something. But, this one's pretty straightforward because now you're away from the sphere. So you can treat the sphere essentially like a point charge. So this is almost straight up Coulomb's law for a negative point charge. Now you're inside the conductor from B to C. So that has no electric field. And now beyond C, you're outside of everything, right? So it'll be like when you do Gauss's law. Yeah, so part B, you are doing Gauss's law for this region. Okay. So in this region, your enclosed charge doesn't change. Your Q in is just negative Q the whole time. So the left-hand side doesn't change because your Gaussian surface is the same. It's still E 4 pi r squared. The right-hand side now, you don't have to do this r cubed over a cubed because you're not changing how much enclosed charge you have. Once you've gotten into this range, your enclosed charge stays constant at negative Q. So imagine then this is just negative Q. Negative Q over epsilon naught is equal to this 4 pi r squared. So actually, I think I can do this. So then in this region, you're doing this Gaussian surface. So then that is E 4 pi r squared is equal to just negative Q over epsilon naught. You don't have to deal with all of this anymore. This is fixed in the range of A to B, this range. Right? So just solve for E. Okay. All right. So, and then part C, you're the conductor, and then part D, you're outside everything. So your net enclosed charge was +1. Okay, it's +1 because plus 2 minus 1, so just +1. So now it's just a positive 4 pi r squared. As opposed to a negative. Okay, now it doesn't ask this question, but when you see a question like this, it is worth making sure you understand what would be the charge on the inside surface, what would be the charge on the outside surface. Okay, think about that for a second. This was originally +2. This is a -1. To cancel out this -1, the inner surface should build up a +1. And so either by conservation of charge or using Gauss's law, if the inside surface has a positive 1, then the outside surface would also have to have a positive 1. Right? So it would be like negative q, or sorry, positive q to match the negative q. So then this would be plus q. So that together, this is plus 2q. Right? That's how the charges will distribute themselves. Any other questions? Yeah, let's take a look here. 30. All right. What's the electric potential at a point indicated by the dot? So very conceptual question here, but it will essentially be 0 because this dot, if it is exactly halfway, okay, I think the assumption here, it doesn't say exactly, but the two halves of the rod in the figure are uniformly charged to plus and minus q. So you have symmetry where all of these charges add to the potential there, and all these charges subtract from the potential there. You should essentially have 0. Wait, Newton's. Newton meters per coulomb. All right. Joules. What kind of. Was it what? Joules per coulomb? Okay, same thing. Oh, I guess I could just say volts. That makes sense. Yeah, volts. 0 volts. Because it cancels out. Does that make sense? Let's see. Since we're not doing RC circuits, we do not need to worry about the last third of the homework. Well, not for the tests, but hopefully as you've been reading through it and as we go over it next week and we do RC circuits in class, you will want to be able to do the problems regarding RC circuits for sure. I obviously, for the sake of time, if you don't want to study them yet, you can save them for later. Yeah, so if the dot was not at the midpoint, yeah, you would have to do an integral, and it would be kind of an odd integral too, because you would integrate from, you would actually have to do an integral on that. Actually, that if it wasn't at the midpoint, well, actually with voltage, it's okay, even if it was not symmetric, because you would have you do some Pythagorean theorem thing, d squared, and you'd have to set your y values accordingly from a shifted y-axis. But I'm pretty sure you won't see anything like that. They really like symmetry. Could you do that problem with the whole line having the same charge? I think we did. The book does that, actually. Pretty sure. It's like, let's see. Does it? Maybe it doesn't. was that in the review packet? I can't remember. But you would do it very similar to how we did electric fields for a line of charge. You would just do potential instead. I can't tell if you're asking if like it's possible to do that problem or you want me to actually do that problem. Yeah, let me see. I think I feel like I've seen that problem very recently. So yeah, here it is. It was a little crazy actually. So this was in the review packet. Yeah, so I put the answer key to this online too, and the outcome of that integral is something kind of crazy. So very unlikely that you'll actually have to calculate that. 28.67. Let's see. Gotcha. This is, let's see, find expression for electric potential distance x from the center rod on the axis of the rod. So that's different because you're not looking for the potential here. You're looking for the potential here. So yeah, we can do this one too. But it's got to be a little different because you don't have to worry about that. Let's see. I think. Let's see. So yeah. So this one, you do your slices. You have some slice here that has some charge dq. It's uniform. We're assuming it's uniformly charged. Doesn't really say otherwise. So dq over dx should equal to q over L, or dq equals 2q over L dx. Okay, and then find an expression. Okay, so this is going to be kind of a pain because each element is a certain distance away from this point. So this point is a distance x. So this separation, we'll call it d, is actually x minus L. I think that's right. X, yeah, minus L. So in other words, the little bit of voltage from this little charge dq is going to be k dq over x minus L. Kind of a pain. Let me make sure that makes sense. What if you have a negative position? Oh, wait. Okay, what am I doing? Think about this. No, okay, sorry. What I want is, I don't want this to be the variable. Okay, I don't want that to be a variable. That's frustrating because it will use x. So we have to use something else. In other words, when I count up my slices, I can't use x. X is, this is going to seem kind of silly, but because x is this distance, and that is what it wants. An expression for electric potential a distance x away. So as I add up these slices, I have to use something else. Let's say that the position of this little slice is let's say little l. Does that kind of make sense? Because I need to add up all of these little slices, and each of those little slices is some distance away from x. So the distance each of those slices is away from x is x minus little l. So that makes sense. It's super confusing that they're using x for this distance. This is a constant. Little l is actually the variable that I'm going to use to add these up. So actually, what I want to say is I can't use slices of x. I'm going to use slices of little l. Yeah, just let me know that's super confusing. I can kind of slow it down and go back and like try to explain it a little more. So this turns into k q over l, big L, d little l over x minus little l. L is my actual variable that I'm going to measure from the center here. Okay, so in other words, this distance away, if I have a negative little l, right, it's like x plus little l, or if I'm going on the right-hand side, then it's shorter, right? So this should account for the actual distance between my little piece, my slice, and this position at x. And now I'm going to add it up. Okay, the total voltage due to this bar is going to be k q over L integrated from negative L over 2 to L over 2 d L over x minus L. And that should give k q over L negative natural log. I think that's right, because the derivative of this, you do the chain rule, there's a negative in there, so you get 1 over. And this is from negative big L over 2 to positive big L over 2. So we should get kq over L of, let's see, natural log of x plus L over 2 minus natural log of x minus big L over 2. Let's just double check something. So what I did was you're supposed to plug this in first and then subtract from this one. But because of the negative, wait, okay, no, I can't do that. Let me take that back. Take all that back. Let's do it. Like this. Negative natural log x minus that one minus, yeah, okay, plus. So the minus, the negative makes this plus natural log of x plus big L over 2. So, okay, so I had it right. Okay, so let's make sure that makes sense. This natural log is an increasing function. So the larger the argument, the larger it is. So natural log of x plus L over 2 should be larger than the natural log of x minus L over 2, which means this is a positive value, which makes sense. And also, I'd have to think about whether this is an increasing function or decreasing, like altogether. But I think this should be right. Let's give it a shot. So KQ over L times natural log. Or is that a function thing? I'm just going to assume that works, but minus okay. Yeah, so this one is a little different from the last one. It wasn't asking for a point on the bisecting line. It was asking for a point on the axis. Questions on that one? I can pull it. It was this thing. Yeah, we're really getting to calculus now. Hopefully you're starting to see a pattern in the way of solving these, though, right? We're looking at some sort of density thing. We solve for the dq part in terms of some sort of differential spatial element. In this case, I had to use dl. Hopefully it makes sense why I use dl instead of dx. You gotta be very mindful and careful about what your variables represent. Any other problems? I think we have time for maybe one more. Or we can just talk about something conceptual. It won't be the same as the electric potential. It'll be the same as the electric potential energy. Also, that the electric potential energy, the total potential energy of the system, is going to be divided into the kinetic energy of each object. So the total kinetic energy of the system at the beginning does equal the final kinetic energy of the system at the end. But since I think the question ends up asking for the speed, you will have to divide that kinetic energy 4 ways. I can pull that one up. Let's see. Yeah, we did this one in class, but I think it was in a different period. So yeah, when you try and figure out the potential energy of the system, you kind of build it piece by piece. You put one charge there, and then how much potential energy do you gain by putting a second charge there, right? So it's under influence of one, and then you put a third charge there. So what is the additional potential energy gained by that third one? Well, it's from those 2 charges, and then you put a fourth one there. Each one, you kind of build it piece by piece. That gives you the total potential energy of the system. And then if they are released simultaneously, that potential energy will become kinetic energy split 4 ways. Any other questions? Yeah. Let's see here. I don't know if I can quickly do it, but I will try. Okay, so start with 1, right? Potential energy is 0. You get a second one. that is 1 centimeter away, right? So actually, let me do it like this. The way I did it in class, imagine that there's this link, right? So that potential energy is going to be KQ1, Q2 over R. Okay, it's positive. They're both positive charges. And then you bring in a second one, and this R. Here, let's do it like this. I'm just gonna call it D. Okay. Whoa. Call that D. Okay, so this one, when I bring this in, this builds potential energy here, and it builds potential energy here. So now I have 2 of these, and I also have this one. Yeah, root 2D. Okay, and now I bring a third one in that has potential energy with this one and potential energy with this one. So now that becomes 4. There's 4 of these links, and also there's this one. So that means there's 2 of these links. Okay, so my potential energy is then 4kq squared over d. It's q squared because they're all identical charge, plus 2kq squared over square root 2d. Okay. That all turns into kinetic energy, which is the kinetic energy of everything put together. So you have 1/2 4 masses times their velocity squared. So you want the velocity, you get 2 over the 4 masses times all this business square root. I think when I did it in class, we did it in terms of potential, and you can do it by potential as well. You do it very similarly. You look at the, you put one charge here. What's the potential at this spot? You put one charge there as that much potential, and then potential here, potential there. You build up all the links. Essentially works out the same way. I think in retrospect, though, actually adding it up in terms of potential energy makes more sense. Last questions? All right, I think I'm gonna call it here then. I'll put the recording up on wherever it goes, somewhere. I don't know where it goes. Yeah, something like that. And I'll put the pictures up onto the Google Drive. So I will see you all tomorrow. Night.